This is the trend of occupational fatal accidents in Japan for the half-century since 1971. In all industries and traffic, the number of fatal accidents declined dramatically to 20% for 50 years. However, in agriculture, we did not have any significant reduction. The recent drop is just due to decline of farmers' population. The number of fatal accidents per 100,000 people for agriculture is 10 times higher than other industries. Number 3. 60% of farm fatal accidents are caused by agricultural machinery. Among them, farm tractors are the worst. In 2017, 157 people were killed by agricultural vehicles. The injured accidents due to agricultural vehicles exceeded 20,000 per year. Based on the number of tractors, we may estimate 400,000 people are injured by farm tractors in the world. Number 4. In 1980s, ROPS was not popular in Japan. Hokkaido University demonstrated the serious importance of ROPS. This experiment was conducted in 1986. Mannequin was put on the seat. Number 5. In mechanical engineering, bouncing ball is the most popular model to explain chaos theory. I purchased this book at UC Davis bookstore. Free fall elastic ball repeating collisions with a moving table. The trajectory of the ball shows very complex motion. 1% difference of initial position evolved exponentially and two balls showed any relationship. This sensitive dependency on the initial condition is the most important characteristics of deterministic chaos. This causes unexpected, unpredicted consequence even with very small changes of parameters. Farmers always say that their accidents were not expected because they were operating as usual. This type of mention is typical in many reports from surveying farm accidents. Farming accidents were usually attributed to trivial things and emphasized unexpectedness and suddenness. I conceived that sensitive dependency of parameters in tractor is key to understand the dangerous behaviors of tractors. Number 6. To validate my hypothesis, I conducted the first experiment with a tractor vibrating subsoiler system after I came back from UCD in 1990. Chisel hits the ground repeatedly with PDO speed. By changing the PDO speed F1, I successfully demonstrated a period doubling bifurcation route to chaos. Probably, it was the very first experiment to detect very clear chaotic vibrations in a real machinery. It was published in International Journal of Bifurcation and Chaos in 1994. Number 7. I moved to TUAT from Hokkaido in 1996 and started to validate the presence of nonlinear dynamics and chaos in agricultural tractors. 5 centimeters height steps located in 60 centimeters spacing as in the photo. At the specific speed matching its natural frequency, very large seat accelerations such as 4G to 5G occurred. And peak accelerations came up to 10G on my body. Number 8. By changing the tractor velocity, we found natural resonance and subharmonic resonance. The subharmonic resonances occurred only in a nonlinear dynamical system. In a 900 kilograms Japanese paddy-filed tractor, we demonstrated the presence of nonlinear dynamics with showing the period doubling root chaos. The experimental results were validated by the numerical experiments with my mathematical model. Number 9. To confirm the presence of chaotic vibration in conventional large-size agricultural tractors, our collaborator Iowa University conducted the same experiment with 3.7-ton John Deere tractor. Resonance jumping was also occurred and the experimental results were as we mathematically predicted. It was Leroy's PhD work and published in International Journal of Bifurcation and Chaos in 2000. We cannot realize the cases of fatal accidents in real space, because it is too dangerous and too much cost. Therefore, we developed a virtual test drive system to study the cases corrected from survey reports of agricultural accidents. This VTD simulated the experiments done in TUAT as shown in slide 7 and 8. Yellow arrows represent acting forces on 4 wheels in 3 dimensions. Axial loads of front and rear became 3 times larger than their static loads. Free fall occurred repeatedly in the periods of 0 vertical acceleration. The VTD results showed good agreement with the real experiments in the mathematical model. We utilized the VTD system to confirm my hypothesis of the sensitivity dependency on parameters for tractor driving. 2 6 cm height bumps locate on the curved road. Blue bumps is 50 cm in front of red bumps. Blue tractor drop its left front wheel to fall. Even with such small bumps, the axial load on the front tire is significantly reduced so that the sufficient cornering force cannot be secured. While the tractor is in the air, the direction of the tractor body can be shifted. After the touchdown, this may cause instability of the tractor. Number 14. The report says that when the operator finished the tillage work on the field and exited through the narrow slope to the paved road, the front wheel floated slightly. With that momentum, the left front wheel stepped off the road shoulder. The operator hurriedly turned the steering wheel to the right, but could not return to its original position. It fell to the field about 2.7 m below. In the VTD, with 0.05 second delay of steering timing, blue tractor dropped left front wheel and overturned in the left side slope. This VTD shows the sensitive dependency on steering timing. Number 15. The mathematical models we have developed were recently published in 2019 and 2020 in Biosystems Engineering, which the best journal for tractor dynamics. Another paper for our novel power hop model was submitted last week to the same journal. Number 16. The photos show the typical type of accidents occurred in sloppy slopes. According to the report, the farmer said that I thought it would be a little slippery because of the rain, but I climbed a narrow slope to cultivate the fields on the slope. On the way, I slipped and the tractor was about to fall, so I stopped the engine, put my foot on the rotary and connected to the cliff side, but the tractor and I fell down 7 m. Number 17. This virtual test drive simulates the cases in the former slide. 4 different friction coefficients between tire and soil were set as 0.7, red, 0.38, orange, 0.36, blue, and 0.2, green. Red and green correspond to very good and very bad conditions, respectively, and both of them have no problem in terms of tractor accidents. That farmer used to go up that slope if the rain was not so heavy. But, at that day, the road surface soil condition was slightly worse than he expected. It means the condition was not orange but blue. As the traction force acting longitudinally reached the maximum friction force in that sloppy slope, there was no friction force to resist the lateral force. Small difference of road conditions bifurcated 2 different consequences such as safe and fatality. This VTD shows the sensitivity on road surface conditions, slipperiness. Number 18. The listed parameters can be sources of the sensitive dependency of tractor behaviors. The sensitivity causes irreproducibility in driving. Therefore, sometime, the ways which a farmer used to do, won't work. They causes a problem in risk management, because it is difficulty to identify the risks corresponding to individual farmer with individual circumstance. Difficulty of risk identification is the problem. To overcome the problem, we propose the strategy self-risk identification. Number 19. Self-risk identification is the approach that farmers can get necessary information to identify the risks in their own farms and working environments. Tractor driving simulator and tractor driving recorder are 2 core technologies to be developed. Conventional driving simulators and driving recorders are useless for agricultural tractors, because the dynamics are quite different between car and farm tractor. We have to specify them to farm tractors. We use tractor driving simulator to find out dangerous and risky situations under given conditions by each individual farmer with VTD in virtual space. Tractor driving recorder is used to visualize the risky events, location, operations form the data obtained farmers' daily operations. This is our current prototype of tractor driving simulator. 2 brake pedals, throttle lever, differential rock switch are implemented in the cockpit. Number 21. From the drone images taken in Fukushima Prefecture, we reconstructed 3D road surface profile and imported to the Tractor Driving Simulator, TDS. TDS can import and synchronize the digital map from Google Earth, Yahoo Map, and other open source. I was able to import UCD West Center's roads from Google Earth. It would be possible to apply our virtual test drive system for UCD Farm, if you could get drone or moving capture images. Number 22. Our tractor driving simulator, TDS, is built up with two popular driving simulation products such as CarSim and CarMaker. They are used to develop ADAS Advanced Driver Assistance System for car. In applying ADAS, the tractor responds to the road roughness in very sensitive ways, as nonlinearity of tractor is much stronger than conventional car. As well as safety driving research, nonlinear dynamics is obviously essential for developing autonomous driving technology of farm tractors. Number 23. This slide explains the role of tractor driving recorder for self-risk identification. In virtual space, we can get data set of vehicle parameters PV and vehicle behaviors BV. Both of them are expressed as vectors. There are many available ways to identify the map F. In real space, we can get data set of vehicle parameters PR and vehicle behaviors BR. We can also get map F. To determine the map F is the key technology to realize drive recorder specified on farm tractors. Number 24. Tractor Driving Simulator, TDS, and Tractor Driving Recorder, TDR, are the two core technologies of the platform. TDS is used to create videos for educational purpose to scientifically explain the mechanism of tractor accidents, many cases, episodes, and scenarios of accidents. The video archive and library will be useful for farmers and schools in any levels. TDS and theoretical model are useful for academic, research and developing sectors. The results from our tractor driving recorder development will give the essential information, criteria, and specification to be satisfied by tractor driving recorder, TDR. This information is useful not only for producers but also for insurance companies. Road design guideline and safety test code considering nonlinear dynamics are expected. It is very important for us, agricultural engineers, to give the concrete knowledge of the mechanism of tractor accidents. Based on the concrete knowledge, we hope that tractor engineers, designers, and farming managers will realize innovative tractor designs and farming systems. We also hope that rational regulations, guidelines, and laws will be established, based on scientific and logical information. Multidimensional and synergistic contributions should be necessary to achieve the ultimate goal. Thank you very much for your attention.